Okay, off we go. So, here's where we were last time. We were talking about path independence, and just a quick reminder, path independence is this outrageous suggestion that somehow the obvious phenomenon of the value of a line integral, depending on which curve you pick, right? Somehow, mysteriously, there are some vector fields for which this never happened. It's crazy. Pick any path you want. Doesn't matter. As long as, now of course, this is with the understanding that you fix and always stick with a single starting point and likewise a single ending point. So any two paths, it's amazing. This is what we would expect, right? We should expect that, well, of course the path matters. But there are some amazing vector fields where it doesn't. And what we saw last time is that, in fact, gradients are the answer to that question. And ultimately, sort of, of course, gradients will answer this question. Think about it this way. If you look at this picture that we have on the left here, what if the vector field is the steepness vector field, right? The gradient of altitude. Right? Well, the line integrals represent altitude gain. And, well, if there are two paths, if there are two trails that get you from trailhead A to destination B, yeah, the same altitude gain, no matter which path you take, of course. Right? So, it's a lovely little revelation of things that start off seeming impossible, turning out to be actually, I don't want to say obvious, but completely unsurprising in retrospect. Let's say that. Okay, all right, and et cetera, et cetera. Okay, so here's where we are picking up. So there is a disappointment with path independence. It turns out that from a computational point of view, it's not that useful. Sometimes it is, but in many cases, not that useful, because let's face it, if you have a path-independent vector field, you're going to somehow capitalize on the path independence. Well, if it's path independent, it's a gradient. If it's a gradient, you can use the fundamental theorem of line integrals. The fundamental theorem of line integrals is already awesome, right? So computationally, we already have an answer we have a really awesome answer. And so my analogy here is just kind of like, in my tools in the toolbox metaphor, it's like, the path independence is a screwdriver. But we already have one of those kind of screwdrivers, right? We already have the fundamental theorem of line integrals. And having two identical screwdrivers doesn't really help that much. Now, there are some counterexamples to that, and I want to be clear about this. To use the fundamental theorem, you do have to be able to identify that anti-gradient. And sometimes identifying the anti-gradient is a fair amount of trouble in some cases. And in those cases, the fundamental theorem is not a good solution, because it requires knowing that anti-gradient, and, well, if that's going to be a pain, then the whole thing is a pain. So I want to show you an example of how to bypass the fundamental theorem in such a case, and that's this example here. So we're going to presume path independence, and yes, that means it's a gradient, and yes, that means there's an anti-gradient, and in this case, we can even see the anti-gradient. I'll bet if you're clever and crafty and you think strategically, you could probably just dream it up, right? But again, the purpose of this example is to show you how to bypass the fundamental theorem in cases where that would have been hard, which it wasn't. But again, as a strategy. So here we go. We have this curve right here. And our vector field is known to be path independent. By the way, how do you know when a vector field is path independent? That's another matter that we're going to talk about very soon. But for the moment, let's just suppose we know, by whatever, magic, right? So, okay, path independent vector field. How am I going to compute this integral? If you think about this, doing this the old fashioned way, we'd parameterize the curve. That's going to bring trig into it. That's going to make the resulting pullback integral full of trig. and those can be inconvenient. So instead, I propose the following. Instead, we're going to capitalize on this path independence. Path independence tells me, look, all I have to do is tie down the start and the end. And now I can pick any other path that I want from path independence, because I know path independence. Any path you want, as long as it starts and ends appropriately, right? So for silly example, I could take that path. Totally cool. Starts at the right point, ends at the right point. All good. Feel free to compute the integral over the blue curve instead of the green curve. It'll give you the exact same answer. And you have a million other options, all sorts of wackiness, whatever. Fine. Obviously, you should pick strategically. You should pick a curve that's as easy as possible. And the easiest curve I can think of that starts at A and ends at B is the straight line segment right here. Right? So because of path independence, I can say that green line integral that I want, I am instead going to compute with this blue line integral, and again, it is path independence that allows me to make that assertion. Now, details to follow, but is everybody on board so far? Okay. And let's see, how much does this help us? How much does this make things better? Now, just to avoid any confusions, we are now fully switched over to this blue curve. So let's just think through how would I compute the integral on this blue curve? Well, you can parameterize. That blue curve is easy to parameterize, but it turns out you don't even really need that. In this case, there is an easy observation that you can make. In fact, even just from the picture, that y is equal to 0. Now, again, that comes up when you parameterize also, but you don't even need to in this case. Looking at the picture, perfectly obvious. Y is always 0. And here's the thing. If y is 0, then that immediately tells me that that coordinate of the vector field is 0. And here's another thing. If y is 0, that also tells me that dy, how much does y change? If y is 0 and always 0, how much does it change? Well, it doesn't change. It's always 0. So dy is 0. And that makes this dot product immediately 0. Game over. We win. No trick. Right? Didn't even really have to parameterize. And all of this, we took an integral that was going to be chock full of trig. It was going to be, I'm going to have to remember those half-angle formulas. Oh, gosh. And it turns into clever observation, boom, done, answer. So it's a pretty neat method in some cases, this being one of them. But again, it does remain. Most of the time, if your vector field's path independent, well, that means it's a gradient, and most of the time finding the anti-gradient's not that bad, in which case the fundamental theorem of line integrals, probably a little quicker. Most of the time I would encourage doing that. Okay, moving along. How did I know that last vector field was path independent? Okay, well, it turns out there's a really convenient little test. The test is this right here. You would like to know if a vector field is a gradient. All you got to do, compute the curl, see if you get 0. If you do get 0, then that vector field is a gradient, and of course we already know gradients are path independent. So that's the beautiful little test, and by the way, you can execute that here. Compute the curl of that vector field. Very easy computation. You do get 0. Boom, done. That means path independent. So that's how I knew, right? Okay, now let's talk about this. Where does this test come from? How do we know this test works? Well, there's a lovely little argument that I've got outlined here. First of all, we've already established that these three conditions are all simultaneous, right? A gradient, we already know appropriately regular, assumptions on the vector field in question. We already know that gradients are path independent. We already know path independent means circulations are zero. Closed line integrals are zero. Okay, that we already knew. So here's where Green's theorem kicks in, and the beautiful thing about it is that Green's theorem tells me that I can compute circulations with double integrals of curl. Right? So since Green's theorem tells me those two things are equal, the left being zero means the right is zero. And now let's look at this equation here. And this takes a little bit of kind of stand back and contemplate to figure out what this is really telling us. Our vector field has a curl with a remarkable property. What it says right there is that the curl, all of its double integrals are zero. Every double integral, whatever domain D you pick, double integral always zero. How many functions do you know that have this property? What functions can you think of that every double integral is always zero? And I claim that there's a pretty short list of such functions, continuous of course, and specifically only zero itself. Again, I think that's a pretty reasonable inference. So altogether, our reasoning goes around like that, and that shows that this does indeed imply that. And likewise, you can take this argument and turn it around backwards. It works just as well backwards, and it tells me that that implies that, which is how we use it as a test. Okay, all right. Now, let's see here. To be clear, what this tells us is that all three of these conditions are equivalent. If you have a vector field for which curl is zero, it's a gradient and therefore also path independent. On the other hand, if you have a vector field where the curl is non-zero anywhere, any single value of R, any point that might happen to give you curl non-zero. If you have any non-zero curl, it is not a gradient and it is not path independent. Okay, so what we're establishing here is the equivalence of these conditions, and therefore a vector field either has all of these properties or none of these properties. Okay. Now, that said, conditions matter, right? And these conditions right here, I need the vector field not only to be defined everywhere, I need it to be C1 everywhere. And we're sailing over some deep water at the moment. There are very nasty little issues that come up if either one of these conditions fails. We have to have C1 on all points in R2. Otherwise, there are some legitimate possibilities of very strange things happening that are kind of hard to see coming. And they're fascinating discussions, and I would love if this were that course that we would talk about such things. But we're going to spend very little time talking about that. So what I'm going to say here is that if any of this fails, then all of these implications here fail, right? And that means there's all sorts of combinations. It could be that the curl is zero, but it's not a gradient and it's not independent. Or it could be that curl is not zero, but it is a gradient and it is path independent. And it could be that blah, 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 right? There's a lot of different possibilities. So very important that we recognize the importance of the conditions. Okay. Now, that said, another take on this is that we can view these three conditions as being equivalent. Again, doff the cap to the assumptions on regularity. Being a gradient is simultaneous with being path independent, which is simultaneous with curl being 0. And let's talk about terminology just a little bit. What should we call a vector field that is path independent? I propose path independent. What should we call a vector that is a gradient? I propose gradient. Some people like to say conservative. Okay, fine, but I feel like gradient was already a great choice. But anyway, I'll let that slide. What are we going to call a vector field whose curl is 0? And there's a great choice for this. Think about what curl means. Right, what's our interpretation of curl? Our interpretation of curl is that it represents, in some sense, how much the fluid is rotating, or more to the point, how much stuff that is floating in that fluid would be rotating as a result of the way the fluid is flowing. So curl is measuring the rotational aspect of the fluid. So if there is none of this curl business, right? If there is no curl, then there is no rotational aspect. And irrotational, I mean, I guess they could have said non-rotational or unrotational, but for whatever reason, the grammar seems to be irrotational. But that's just a representation of, there is no rotational aspect to the fluid. So this is a very, very natural choice of terminology. And with this established, irrotational and gradient and path independent are all simultaneous for nice vector fields. Again, appropriately regular. Okay. All right. Okay. How we doing? Everybody on board? Okay. Let's see here. There is a very similar test in 3 dimensions. Here's our test in 2 dimensions. There's a corresponding test in 3 dimensions. If in the same way that in 2 dimensions, now in 3 dimensions, if you want to know if you have a gradient, right, the way that you test that is there is an operator that you look at to see if it's 0. It's a very, very similar test, right? The only difference is that, well, it's a slightly different operator. Here, this is 2-dimensional curl, which sometimes I like to call Green's operator, right? And which we have a notation which is del wedge, right? And there's various different, ways of thinking about it. In 3 dimensions, it is this, I'm going to call it a different operator because it's certainly different in some important ways. We still call it curl, right? But we write it as del cross, which we can't use that in 2 dimensions. It doesn't make any sense in 2 dimensions. By the way, 3-dimensional curl is a vector valued operator. 2-dimensional curl is a scalar valued operator, right? So there's some significant differences between these. It's always kind of rubbed my fur backwards to call these 2 noticeably different operators by the exact same name, calling them both curl. But that's I grumblingly get over that, and it's just the 3-dimensional version of curl. Now, how do we prove this highly analogous theorem? Well, it turns out in a highly analogous way. Green's theorem was the big trick that allowed us to prove the 2-dimensional theorem, and there is an analogous theorem we haven't covered yet that's going to allow us to prove the 3-dimensional equivalent. So that's a little bit of foreshadowing. We will revisit this in a bit, but just for your anticipation purposes, when we have the appropriate tools, we will revisit, and the way we will prove the 3-dimensional theorem is a shameless copy, total piggyback off of the way we prove the 2-dimensional theorem. So that's just something to keep an eye out for. Okay, so let's use these tools, and let me clean up my mess here, by the way. Get all of that. Okay, so let's ask this question. Here's a vector field. I would like to know, is that vector field a gradient? Well, what that means is, this is what I want to know. I want to know if this vector field is a gradient. By the way, notice we're in 3 dimensions because the vector field has 3 coordinates. That's why I know we're in 3 dimensions. That's why I'm using this theorem, or I guess here, let me just be a little bit more compact. That's why we're using the 3-dimensional theorem, because we're in 3 dimensions. How do I decide? Well, it says right here, I need to compute the curl. All right, so we're going to compute the curl. My goal will be to ask whether that curl is or isn't 0. Right, so here we go. We're going to compute the curl. The reason I'm computing the curl is because I wanted to determine is it or is it not the 0 vector. So we begin with the computation. By the way, make sure you're good at this. Make sure you can compute curl. Right, so the formula is strongly suggested by that notation. It's also written down explicitly in the chapter 3 part of the lecture notes and in the book, and it's probably in the book here in chapter 6 or 7 anyway as well. And you start computing, and here's the very first coordinate you write down, which we can already see is not 0. Right? Now here's the thing, if you want to show that something is the 0 vector, you need all 3 coordinates. All 3 of them have to be 0. If you want to show something is not 0, any coordinate not being 0 is good enough. Right? So, kind of a clever observation. I don't even have to finish this calculation. I can already see, just from having computed one coordinate, that this, this curl here is clearly not going to be 0. It's just not going to be 0 everywhere. It's already not 0. I don't even have to compute the second and third coordinates. So because we know it's not 0, we also know from the test that this vector field is not a gradient. And by the way, when you have, once you know that it's not a gradient, once you know that there is no anti-gradient, don't try to find it. It's a complete waste of time. We know it's not there, right? It's a wild goose chase. Don't try. It's not there to be found. Okay. All right, let's see another example. Let's see a 2-dimensional example. Here we go. I want to know if this vector field is that or is that not a gradient. And we're going to play the same game. We're going to use the local test. If you want to know if a 2-dimensional vector field is or is not a gradient, we're going to compute the 2-dimensional curl. We're going to see if it's 0. And here we go. Compute the 2-dimensional curl. Yada, yada, yada. It is not 0. So there is no anti-gradient to be found. Look how easy, right? Super easy. Couple of quick partial derivatives. Couple of the world's easiest derivatives to compute. And boom, we have an answer. It's not a gradient of anything. By the way, there's some satisfaction to be had in thinking about this geometrically. Y'all will recall we've seen this vector field before. That vector field looks like this. And if that were a gradient, let's just think it through. If that were a gradient, what would that tell me? Keeping in mind, gradients always point uphill. Right? What mountain have you ever seen where that's a collection of arrows that are all pointing uphill? It doesn't make any sense. How could all of those arrows point uphill? If all of those arrows pointed uphill, then as I walked this path, I would have gained a positive amount of altitude. How can I start and end at the same point and be gaining altitude the whole time? Right? That's the old classic joke that grandparents used to tell their grandkids. I had to walk to school and it was uphill both ways. No, it's nonsense. It doesn't make any sense. Right? Okay. By the way, Escher stairs, right? Uphill as you go around an entire loop. That's not possible for the same reason that is not possible. Okay. All right, so this is about the strategic diagram. This is stuff that I think is really, really useful. It's really wonderful for a combination of reasons. My own personal interest in the diagram is that it is a glimpse into some very sophisticated ideas that are really the fully powerful and best way to treat all of this material. That's too advanced for this course. It would be quite a bit too much, really, to be able to talk about. A full treatment of all of this is extremely sophisticated math. I would call it late undergrad at the earliest, maybe mid-grad school kind of experience. The stuff that we're talking about here gets it gets into some pretty sophisticated stuff. So that we can't see. But this diagram has a lot of the sort of the boiled down, the bones, the structure of good ideas of this diagram comes from those very powerful, sophisticated ideas. And I like it for that reason. But I also like it, and students like it, because this is a guide. This will help you make good decisions. Now, the way I drew the diagram here was with the intention of being compact. There's a more full and spacious, more complete, arguably easier to work with version in a PDF file that I've got. Come to think of it, it's on the website, and the website's down. I will try to remember. Feel free to remind me if I fail to put this diagram in the Google folder that I've created as our little temporary workaround while the website's down. So anyway, here it is. Here's this diagram. And I claim that there's a lot of nice things that happen when you draw the diagram this way, when you place the various players that we've discussed so far in this class in order as they lay out here. For the following reasons, and let's think about these operators. Y'all know the gradient operator takes a function, gives me a vector field. Y'all know Green's operator, aka curl, takes a vector field, gives us a real valued function, scalar valued function. Composing them has this nice feature that it's an exact sequence. Appropriate regularity assumed, right? Gotta worry about that. But what we mean by an exact sequence, and I kind of talked about this a little bit, I'm not sure if I used that term, but back in chapter 3, we were talking about everything having a lifetime of 2. So if you have some function, and if you compute its gradient, that will give you a vector field. Yeah, fine, cool, but when you take curl of that, you will get 0. Lifetime of 2. Birth, survival, death, if you want to go with the metaphor. Okay. So, it's kind of neat to know that that's true, because very often we have a vector field that for whatever reason we know to be a gradient. And once you know it's a gradient, boom, you don't even have to compute curl. You already know curl is 0. Works the other way as well. If you have a vector field and you compute curl and you get 0, that tells you that yes, there is an anti-gradient. And that's that local test that we just talked about a bit ago. Okay. By the way, it also works as follows. If you have a vector field and if you compute curl and if you don't get 0, if you get a non-zero function, well then, how could there be an anti-gradient? If there were an anti-gradient, hypothetically, if there were an anti-gradient, that would give you a lifetime of 3, which is not how it works, right? Again, now I'm not proving anything here. I'm just asserting. I'm developing this kind of metaphor for how to think about these things, and we're not allowed to have a lifetime of 3. So therefore, we know that this thing couldn't possibly exist, aka there is no anti-gradient. They're kind of cool. By the way, if you want to play around with the idea, something analogous happens here when you're thinking about boundaries of regions. And it's a fun little game. Think about any two-dimensional region. Think about its boundary curve. That boundary curve
If you ask where are its endpoints, there aren't any. There is no start or end. And I mean, you can kind of make one up as you choose to parameterize or something, but there is no intrinsic starting point and there is no intrinsic ending point, because it's a boundary of a region, right? It's like if you have a fenced off region, that fence does not just abruptly end somewhere, right? It's got to kind of loop back around on itself. So there is a similar kind of a lifetime thing. Said differently, if you have a curve and if it has a starting point and an ending point, such as here's a starting point and then it's got an ending point, then it's not the boundary of a region. Right? So totally analogous. Totally analogous. There are little asterisks that can be resolved that we're not going to worry about. Okay. Here's another cool thing about the diagram. This is an eyebrow raiser, I think. Let's talk about the fundamental theorem of line integrals. Fundamental theorem of line integrals says that if you have a vector field, if you have a function and you compute the gradient of that function, and if you have a curve, and if you look at the endpoints, starting and ending points of that curve, and if you evaluate the function at those endpoints, like so, and if you look at the line integral of the gradient on the original curve, like so, you get the same thing. Okay, now, not particularly impressive. Let me streamline this, the notation here. Not particularly impressive. I mean, we already knew that every operator, every player that we've been discussing concerning this stuff is on the diagram. So all I'm really doing is kind of chasing around, following where I've seemingly arbitrarily put all these players and operators. So the fact that it looks like something is not that interesting. Here's where it gets interesting. Let's do the same thing for Green's theorem. Green's theorem says if you look at a vector field and compute its curl, if you take a two-dimensional region and look at its boundary curve, then the line integral of the original vector field on that boundary curve, like so, and a double integral of Green's operator over the original region, like so, are always equal. So said differently, Green's theorem has the exact same sort of structure, the exact same layout, you might say, on this diagram. Now, like I say, at this point, I hope that's an eyebrow raiser. Like, wait a minute, wow. Neat trick at a minimum, right? That I was able to lay out these various operators and players in such a way that these totally different theorems with totally different geometric contexts, totally different physical interpretations, right? Totally different geometric interpretations. Diagrammatically, they look exactly the same. It's pretty cool and pretty unexpected. Now, one reason you might be a little bit less surprised by this, we already knew that these were both accumulation theorems. We already knew that they were kind of copycatting this idea of the whole being the sum of the parts when you have an accumulating quantity and resulting density, blah, blah, blah. All right, so there was all that. But still, I think it's kind of wild that a theorem about change and a theorem about circulation structurally look so much alike. And by the way, this is not the end of that little story. What we're going to see in chapter 7, and this is just a little foreshadowing, what we're going to see in chapter 7 is that there is a three-dimensional version of this diagram. Now, don't worry too much about this right now because there's a lot of stuff on here we haven't talked about. I haven't talked about this at all yet. Y'all don't even know what that is. Don't worry about it. We haven't talked about these theorems at all yet. Don't worry about that for the moment. Okay? But just as a preview, just so you know what's coming, this diagram where I take the fundamental theorem of line integrals and interpret it as a little diagram chased like so. Oh, come on. Hang on a second. The exact same diagram, Chase, works for what we are soon to discover as Stokes' curl theorem. And furthermore, the exact same diagram, Chase, also works for what we're going to soon see as Gauss's divergence theorem. So this is not a minor little bit of cleverness. What you can see here is that all these theorems truly are basically the same theorem. Structurally, they lay out on the page. Again, if you're clever enough to arrange the objects on this, in this discussion, lay them out in this exact way, and it's very important that they be laid out exactly this way, then these tremendous patterns show up. So here's another one, by the way. I'll remind you that if you're looking at a special vector field. Now, the special vector fields are the ones we were just talking about, path-independent vector fields that are also gradients, that are also irrotational, right? This very cool category of vector fields. We can represent them like this. That is what it would look like to say that they're gradients. This is what it would look like to say that they are irrotational, that curl is 0. And here's how I like to represent the idea that they're path independent. Path independent means that if you have two curves with the same starting and ending points, same boundary points in other words, that they'll give you the same value for the line integral. Now that's just how I like to draw path independence on this diagram. So again, not that impressive, okay, yawn. They had all these ideas had to show up on the diagram one way or another. Here's where it gets impressive. See if I can get that. This pattern that works on the two-dimensional diagram works exactly the same way on the three-dimensional diagram. And here's where it gets even weirder than that. It also works one position over. This isn't just increasing the dimension of the context. This is increasing the dimensions of all of the objects involved. It's not even about gradient anymore. Now it's about curl fields. It's not about fields whose curl is 0. It's about fields whose divergence is 0. It's not about path independence. It's about, what will we even call something, we don't even know how to describe what's in orange there because we don't really have the tools yet. We don't know what there's some sort of a double integral happening there that we've never seen before. But there is an analogous to path independence idea to be had, and that's extremely powerful and extremely useful that we will be seeing. So again, I think the fact that this pattern holds like so, I think is truly wild. And anyway, this is all foreshadowing. We're going to see all of that more as we get into chapter 7. Be on the lookout. I strongly support the idea that as we go through chapter 7, you should have this diagram front and center, right? Print it out, tape it up to the wall next to your desk or wherever you study. Every single thing that we do, glance over at the diagram and just kind of get your bearings and think about everything that we're doing in terms of where it fits in on the diagram. And it will just make the pieces fit together in powerful ways. You're going to notice patterns and analogies that are just extremely useful. This is the best way I have ever seen to organize all of these ideas in your mind. And it cuts the workload in half, maybe third. It's a dramatic, helpful tool. Okay, all right. Okay, moving along. Let's see. Let's try that again. Okay, so as promised, I promised a bit ago that I would show you how to find antigradients. I've pulled a couple of rabbits out of a hat so far in this discussion, where I just here's the antigradient out of thin air with no clarity on where I got it from, right? So now I'm going to show you that trick. It's actually pretty straightforward if you think it through. It's not that surprising. If you want a vector field to be a gradient, well, that vector field has coordinates. Gradients are computed by certain formulas making up their coordinates. And so if the field is going to be a gradient, well, what that means is one coordinate at a time, right? The coordinates of the vector field have to be partial derivatives of the antigradient. No, that's what it means to be a gradient. Right? Now let's look at these three equations. Let's think about what they mean. Y'all remember, I'm sure, from long ago, if you have, okay, let's see how to say this. If the derivative of g is f, then g is the antiderivative of f. Right? I mean, so you get it's the same statement. If this is a derivative, then that is an antiderivative. Right? So I'm going to do the same thing here. This, what I have in purple, says that P is the x partial of f. This just says f is the x antipartial of P. Same statement, really, pretty much. Right? Just saying it backwards. And then likewise here, likewise here and likewise here. Right? So we have these three statements, but wait a second, what about the integration constants? I'm sure y'all remember integration constants. After all, I mean, if you add a constant, it doesn't change the derivative, and so when you're writing down antiderivatives, any constant you add in is kind of for free. Here's the thing. If we're talking about f being something like this, and let's think about what restrictions does that put on my constant over here. What can I say about that constant? Well, really, all I need is for that to disappear when I take the x partial. So anything, not only constants, but anything whose x partial is 0 will likewise not mess up the requirement, and therefore is okay. So any, not only constant, but any what we call partial constant, anything whose partial with respect to x is 0 is free, and you can add it in totally fine, and it doesn't mess up a thing. So that's the difference with compared to single variable. These partial constants don't have to even actually be constants. Okay. All right. So if you can find some function that is all three of these things, then that function will have the correct gradient. Okay, so that's the big idea. So thus begins the game. What we're going to do, the way we're going to find antigradients, is we're going to compute the appropriate antipartials. We're going to give ourselves the flexibility of choosing partial constants however we might find convenient, and then the goal is to find a single function that's equal to all three of these things, and if we can pick those partial constants to make this work, then sweet, we just found ourselves the antigradient. So let's do it. Here we go. Here's a vector field. By the way, you can confirm for yourself. Good calculation. Everybody should do this. Let's take 60 seconds. Right. This is a very quick. Just go ahead and compute the curl of that. Right? You're going to get the 0 vector. That's good. You compute the curl, you get the 0 vector. That tells you that this vector field is a gradient. That tells you that there is an antigradient to be found. And again, it's good to know that you're not off on some wild goose chase. It's good to know that the antigradient you're looking for actually exists, so you're not going to just be endlessly searching for the impossible. Okay. All right. So, the rule, first coordinate, take the x antipartial. Second coordinate, take the y antipartial. Third coordinate, take the z antipartial. All of this right here is what we were talking about right here. right? X, Y, and Z antipartials of P, Q, and R respectively. Oops. And you can punch those up. Y'all are experts at antipartials, right? It's just like antiderivatives. It's just where you treat the other variables as constants. Don't forget to add in your partial constants. And thus begins the game. And again, I remind you, the goal here is to figure out, is there some function that's equal to all three of these things? More to the point, can I choose these partial constant functions in such a way that all three of these things are equal? Okay, so again, game. Let's see here now. Well, I see an x squared y term there and there, but unfortunately I don't see an x squared y term there. Now your first reaction is going to be, oh, well then they're different. They have different formulas. They're different functions. Come on, we lose, right? There's no way forward here. But don't forget your partial constants. You're allowed to pick this to be anything you want toward the goal, hopefully, of making all three of these things equal. So what function of x and y might I want this to be? And I think x squared y looks like a great choice. Because if I make that x squared y, then there is an x squared y in all three of those expressions. And that's what I want, right? I want all three of these expressions to be equal. So then likewise, I see an xz, I see an xz, I don't see an xz there. Oh no, that's too bad. Oh, wait a minute. I could just make that xz. It's allowed to be any function of x and z, and I think xz is going to be a helpful choice. So let's do that. Now I've got xz in all three expressions, and then you can see where this is going. Minus yz squared, right? None here. Oh, wait a minute. Maybe it is. Yeah, check it out. That first partial constant, any function of y and z, and minus yz squared, totally allowed. And so, as required, we have found allowable partial constants that make this equal to all three of these things. And that is my anti-gradient. And a healthy little exercise, and again, this is a very, very quick thing to do. Check it. X partial, Y partial, Z partial is what it's supposed to be. Okay, how are we doing on this game? Does everybody see how the process works? Any questions about that? Okay. As it should, this will fail if there is no anti-gradient. Now, again, let me just to be clear. If there is no anti-gradient, we don't want to find one, right? If there isn't one to find, we shouldn't find one. We want our system to fail if there is no anti-gradient. So here's such an example. There's a vector field. The curl is not 0. There is no anti-gradient, and I have a typo here. Shame on me. Sorry. This that should be little f. It's the anti-gradient that should not exist. Sorry about that. You might want to fix that in your copy of the notes there. And it's just oopsie. So let's play the game. Let's confirm that the game will fail. And so, okay, we take the appropriate antipartials. These are the antipartials. Let's see here. I get to add in partial constants. I would like to, in theory, I would like to be able to make these two things equal to each other by picking appropriate C1 and C2 functions and give it a try. You're going to fail. It doesn't work. There is no way to make a function of y, called C1, and a function of x, called C2, that will make these two things equal to each other. Can't do it. Right? And I think it's actually pretty satisfying, pretty clear. Again, just try. Right? And what you're going to run up against pretty quickly as you try is that you just can't make it work. So again, this is good news. It shouldn't exist. we shouldn't have found something, so thankfully we didn't. And by the way, this is what it'll look like when you try to find an anti-gradient that isn't there. Again, this process doesn't just magically produce anti-gradients. Okay, let's see here. We are, in fact, out of time. So what a perfect place to end. We just finished 6.3. Y'all have a great weekend. See you on Monday. And fingers crossed that the server comes back soon.